Hello there, Energy 301 students. Dr. Shragi here, and I thought I'd just walk you through an example of how we would do some inferential statistics and how we would test a hypothesis and so on. I'm going to be using that OPPD data we're going to have. Remember in Project 3 there was a question that just asked you to compute the average power consumed on the grid for weekdays and for weekends. Now when I wrote that question, all I wanted you to do was come up with two numbers, average power on the weekend and average power on the weekday. Even though that made me kind of unhappy because I knew this material was coming. You're going to get one number is going to be bigger than the other. Unless some miracle happens and they just happen to be exactly tied, one of those two values is going to be bigger and one's going to be smaller. It's the business of inferential statistics and hypothesis testing to find out, is that bit difference big enough to care about? So what I want to show you is how to actually do a difference of means test, like what we were doing in all the lectures now. In the lectures we were doing it about heights of Creighton students and heights of UNO students. This is a little bit more applied to the ideas of electrical load and yield, of course. So I just wanted to show you real quick. I made some little programs here. If I go in, I'm going to use VI instead of Nano, but it works the same sort of way. It's just a text editor. If I look in, and I made a program called example.mat, and all this program does here is it loads that OPPD data that we have, and loads the statistical package. All I did here was I created a new array, I called it holder, that has, it just has two columns and as many rows as are in that OPPD electricity data. And I just moved into column 1 of that data the is weekday variable. Remember, that was a variable that was just equal to 1 if the observation was taken on a weekday, and 7, strangely, if it was taken on a weekend. So that's going to be column 1 of this holder array. And then I just moved the electrical load data into column 2. So now I have a big array called holder that has tens of thousands of rows and 2 columns. One is just a flag as to whether it's a weekday or not, and one is the actual electrical load and yield. I did go so far as to actually filter out the bad data, as one really ought to. I think in practice there was only 4 bad observations in the whole data set, so it wouldn't have really destroyed things if we didn't do that out. And then what I did is I filtered out the weekdays into a new array, using my logical indexing. I filtered out and I made a new array called holder weekday that just contains the electrical load data for the weekday. And I did the same thing for weekends. I have an array now called holder weekend that just contains the observations of electrical load on the OPPD power grid on weekends. Now, we have this statistic that okay, let's make our hypotheses here. First, let's do that. Okay, we want to know if there's a difference between the electrical load on the grid on weekends versus weekdays. Our null hypothesis is going to be that the mean power used on weekdays is equal to the mean power being used on weekends. That way, our alternative hypothesis is that these two are not equal to each other. Remember, we want these two hypotheses, H0 and HA, to be exhaustive and mutually exclusive. Well, there's no other option. This is definitely exhaustive, right? Either the two are equal or they are not equal, the two means. And they are mutually exclusive. One has to be true and one has to be false. Okay? Now the way we decide how we're going to make a decision about whether or not we're going to reject a null hypothesis has to come to us from the business of a test statistic or an inferential statistic. And all through this module we've been using as our example, we've been using the Z statistic. The Z is the so-called test of the difference of two means. There's a zillion of these kinds of things out there. And here's the equation for it, now corrected to have a plus sign in the denominator. It makes me mad that I've been having that negative sign all throughout this module. And, alright, so that's our test statistic. Okay, the numerator is just the difference of the two averages from our sample, and the denominator has a square root, and then there's stuff in there like the variance of one sample, and the sample variance of one set of data, and the one sample variance of the other. Now, it's still marked on their UNO and Creighton, but now it's like weekend and weekday. Okay, that's just our two groups that we're doing there. Alright, so I computed, with my Octave program here, I computed the mean power on weekdays, just by taking the mean, average. Octave oddly uses the word mean when the correct word is average. for weekdays, and I did the same thing for weekends. So now these are just two numbers, and it'll be printing them to the screen because I don't have a semicolon at the end of this line. And then I'm going to compute the variances of the samples, because that's in there, and I called it weekday var and weekend var, and you can see that they're just the variance, the sample variance, which is var in octave, of the column 2, which is where the electrical load data in megawatts is stored for weekends and for weekdays and weekends. Fantastic. I also had to compute the sample size. N for each of the two groups is in that equation as well. Notice that I did it by just counting the number of rows in the holder weekend and the holder weekday. That seemed to be the lowest, the easiest thing to do. And again, these quantities, I all have them here without semicolons on the end of these lines, so that we can, so that we will get them printed to the screen without having to do anything extra. And then here's my equation for Z. Okay, this is the same equation that we've been using corrected now, so that it has a plus sign in the denominator to compute the Z statistic. All right, so let's actually run this program here. I'm going to break out of this, and I'm going to launch Octave, and I'm going to run this example mat. All right, so on my computer I have to use Octave CLE. It's a slightly different thing, but whatever. It's the same thing, same sort of thing. And I'm going to run example.mat. And my result here is that when I did this for all the data in our information that OPPD kindly provided to us, we end up with the weekday average is, 1,262 megawatts. And our weekend average, weekend bar, was 1,185 megawatts. We apparently are using, at least it seems as though we are using less electricity on the weekend than on the weekday. You can see that at this time that is 30,044 observations on the weekdays, and that is 5,000 observations on the weekend. And the result is that the value of the Z statistic is 21.61. That's a big value of Z. If you remember, to manage our risk of a type 1 error, we're going to define a value of alpha, the probability that we're going to make a type 1 error, that we're going to reject the null hypothesis when the null hypothesis was actually true. All right, well, if you might remember, a typical value of alpha is 0.05. We accept a 5% chance risk of making a type 1 error. And the value of Z, that critical threshold value of Z corresponding to an alpha value of 0.01 was, 1.96? In other words, any value of Z that comes up from this test bigger than 1.96, we can say that we can reject the null hypothesis with a significance level of 95%. There's no more than a 5% chance that we are rejecting the null hypothesis incorrectly. Well, we're way out beyond 1.96. We're at 21.62. Wow, we're way out in the tail of the distribution here. We can definitely reject that null hypothesis. I mean, good grief, we used the 95% level. We could have used the 99% confidence interval. I think that, if I remember right, the threshold of Z for 99% confidence interval, what is it, 2.57, I think? So if the critical value of Z corresponding to a 99% confidence interval is 2.57, so anything bigger, any value of Z you compute being bigger than 2.57 means that the value is statistically significant at the 99% level, meaning there's no more than 1% probability that you are rejecting the null hypothesis incorrectly. And in fact, oh my gosh, we're way out in the tail of the distribution. Why? Why did we end up with such a high statistical significance? Well, these samples are huge. 30,000 weekday and 5,000 weekend observations, when the difference seems to be about 80 megawatts. Well, 80 megawatts is about almost a 10% difference between the two groups. Wow, we ended up, I mean, there's no doubt. Strictly speaking, we haven't proven that Omaha uses more power on weekdays than on weekends, but the probability of a type 1 error here is minuscule. The p-value of this test is, millionths of a percent or something like that. But it's mainly because that sample size is so big. So I'm going to show you what I did to kind of make some interesting ways to kind of play with this. I made a slightly different version of this program example called example, did I make it 10? Yes, I did. The next one is 10. Okay, those sample sizes are huge. What if we had 10 times less data? Like instead of taking all these observations, we only took every 10th observation. Now, it's a little bit of a nifty little trick how I got Octave to do that. How I got Octave to, instead of using all the data that came in from the OPPD electricity data file, I now am using every 10th observation. But it'll reduce the size of n for weekends and n for weekdays 90%, right? We have a much smaller sample here. But everything else about this program works exactly the same. It's just these little tricks I use to get Octave to ignore most of the data. And now, if I go into Octave and I run this new version of the program, example10.mat, I get new results. I get a very similar, but not exactly the same value of weekday bar and weekend bar, because, I mean, this is a different sample. Different numbers are going into this average than were going into the original average, which had all the data in it. And you can see, for example, that the new sample size is only about 3,000 for the weekdays and only about 500 for the weekends, because we're not taking all the data. We're only taking every 10th observation. And our new value of z is significantly smaller. It is 6.7. Now, don't get me wrong. 6.7, a value of z of 6.7 is still way out in the tail of the distribution for the bell curve. I mean, when I showed you those bell curves, you know, the end of it on that graph there was about z equals 3. I mean, that curve just tails off to infinity, but I mean, it gets closer and closer asymptotically to the zero on the way. This still is statistically significant at the 95% level. It's still statistically significant at the 99% level. It's probably statistically significant at the 99.9% level, meaning that like there's only a 1/10% chance that we may be rejecting the null hypothesis incorrectly. But overall, this is still a really amazingly high value of z. Why? Because these samples are still pretty big. I mean, we still have 3,000 observations of the electrical load on the grid on weekdays, and we have about 500 observations on the weekends. Let's try it again. I made a slightly different version of the program. This is called example 100. And example 100, instead of pulling out every 10th observation, pulls out every 100th observation. So now, compared to that original calculation that used all the data, tens of thousands of observations, we're only taking every 100th observation out of there, and we'll get a much smaller sample size. Okay? So again, all that's different here is I made this magic little trick here that extracts just, instead of reading all the data from that file, it only is reading out every 100th observation. But that's not, you know, anything, that's just a little bit of Octave magic, okay? So if I go back in here and I run Octave, I launch the Octave interpreter, and I run this new version of the program, which is called example100.mat. Hey, okay, we get, again, a slightly different version of the average for the weekday, and we get a slightly different average for the average of the weekend, and we get smaller sample sizes. Now we only have about 300 observations in the weekdays, and we only have about 50 observations on the weekend, and we do have a smaller value of z. We're less confident. Don't get me wrong, that value of z is still huge, 5.95. That's way out in the tail of the distribution, but nowhere near as far out in the tail of the distribution as it used to be. We're still really confident that there's a difference between the electrical load on the grid on weekdays and weekends, but we're not quite as confident as we were before because the sample sizes are getting smaller. I mean, I only have 50 observations on the weekends rather. All right, that was if we took every 100th observation there. What sample was even smaller? We didn't have so many data. I'm just going to go ahead. I'm not going to show you. I made versions of this with lots of different sample sizes. And one of them that I made is picking every 300th observation. Okay, so again, our sample size is even now 3 times smaller than it was before, and if I run it, again, we get a slightly different version value of the weekday bar. We have different values going into the calculation of our average. In fact, now we only have 100 observations on the weekday and only 17 observations on the weekend, and we can compute the z statistic based on those 17 weekend observations and those 100 weekday observations. And you get a value of z of 2.9. Now 2.9 is still pretty far out in the tail of the distribution of the standard normal curve. For example, the threshold value of r, of z, for a confidence interval of 99% was 2.57. So this is even higher. I mean, we have higher confidence than 99% that we are correctly rejecting the null hypothesis and accepting the alternative hypothesis that the the electrical load is different on weekends than on weekdays. But we're not as confident as we used to be. Okay? I mean, it's still statistically significant, but as the sample sizes get smaller and smaller, I'm less and less confident that I know what I'm doing, that I have an adequate sample that adequately represents what the real power consumption on OPPD's grid looks like. All right. Well, I actually have other ones I've done too. That was 300. I also made a version where I am running the same calculation, except now I am only taking every 1,000th observation. I'm just trying to make the sample size smaller and smaller. It was the easiest way to do that. Just to give you an example here, okay, now we're taking every 1,000th observation. That means that there are only 30 observations on weekdays that go into this calculation. From that giant database of 30-some thousand observations of the electrical load in Omaha, we're only pulling out 30 of them on weekdays, and we're only pulling out 6 observations now on weekends. And we get a new, based on those 6 observations, we can compute a weekend bar, the average power of those 6 observations, and we can compute all this, and we get a value of the Z statistic of 2.05. Oh, well, 2.05, that's actually statistically significant at the 95% level. Remember, the threshold value of Z for the 95% level was 1.96. So we have a greater value of Z than that. So there is no more than a 5% chance that we are making a type 1 error when we reject the null hypothesis here and accept the alternative hypothesis that the electrical load is, the mean electrical load on weekends is different from the mean electrical load on weekdays. But here's the deal. This is not as high. This Z value here is not reaching the value for 99% confidence. In other words, remember that critical value of Z was, I think, 2.57. So there is a greater than 1% chance that we are making a type 1 error. Okay? That we are rejecting the null hypothesis, and the null hypothesis was actually true. Now, in this case, it's because the samples are getting really small, right? With only 6 observations of the electrical load on the grid on weekends, we aren't very confident as to that we have a very representative sample here, and that's why the confidence in our result is getting smaller and smaller. So at this point, we are still, even with this really tiny sample though, we are still have confidence at the 95% confidence level that we are correctly rejecting the null hypothesis, but we don't have it at the 99% level. There is greater than a 1% chance that we are incorrectly rejecting the null hypothesis when our sample was this small. Why not break it even more? I went ahead and did one more thing. I went ahead and I made a version where we are pulling out only every 2,000th observation. Now our sample sizes are just ridiculously small. We only have 3 observations of the data on the weekend. We only have 15 observations on the weekday. We still can take those 3 observations and take their average and get the weekend bar, and we can take those 15 observations on the weekdays and make weekday bar, but our confidence is not very high anymore. In fact, the computed value of the Z statistic is 0.22. That's not statistically significant. Remember, our threshold, like for a 95% confidence interval, was a Z value of 1.96. We're nowhere near that now. We're kind of near the hump of the distribution. So what we're saying here is we have such a small sample here, we don't really have very much confidence that the 3 observations of electrical load that we took on the weekend are really all that representative of the real process of how much is the electrical load on OPPD's grid on weekends. So we don't have very good confidence in our results anymore. This result is no longer statistically significant at either the 95 or the 99% confidence interval. Under these situations, we cannot reject the null hypothesis, and we have to just say that we don't have enough information here to reject the null hypothesis. Cool. All right. Well, I just thought I'd show you a little demonstration like that. If you have any questions about how this works, please let me know. This has been Dr. John Schrage.